I'm Mohammad Siddique. My presentation is on share price prediction, which can be used for share trading using LSTM and price trend or price movements. So we'll discuss the context a little bit elaborately because I myself was not expert on share trading. And if there is anyone who is not expert on deep learning, I will go through that one. So context a little bit heavy. So the context is a little bit heavy. Then we'll do the motivation. We'll see the data and its status a little bit. Then we'll discuss the trends and the models, and we'll discuss the results. So what is a share? A share is a piece of company. Company sells a piece of its ownership to acquire capitals from the share market. And worldwide, there are more than $74 trillion of shares in the different markets. And every day, around $280 billion of shares are exchanged in the share market, weekdays only when the share markets are open. And people invest in share because it gives a good return. On an average, in last 30 years, share investment has been like 10% per annum return provided. So it's a good amount, a good investment. That's why people are invest in shares. Now, who invest in shares? Like everybody, people, companies, then retirement funds, all these financial institutions invest in shares. So in the market, the actors we can divide in roughly three categories: buyer or sellers, who are the investors, brokers, and stock exchange, and regulators. Now, there are two basic ways to earn from share. One is investing and one is trading. Investing means you buy a share, wait for its price to go very high, or earn the profits from the dividend, which is the profit earned by the company, and give a share of that to the shareholder. Or the traders who buys a share for a very short time and sells the share as soon as it gets a little bit of profit, target matched, sell it. And they sell it very quickly. The traders are my target group for the price prediction because I'm predicting the price in short term. So why share price changes? Mostly due to the fact that people want to buy a share. If share is performing well, everybody wants to buy the share. Demand increases, the price increases. But there are underlying fundamentals why the share price increases. Mostly if the value of the company rises, the share price should rise, and that happens. But share price are not the share value all the time. The value can be a little bit less or more than the price. If people want to buy that share, the price will jump. If people don't want to buy the share, even if the value of the company is good, the share price will fall. There are macroeconomic factors, and there are other factors, geopolitical factors, wars and droughts and all these things are there. So why we want to predict the price? Because if we predict the price properly and correctly, we're going to make a lot of money. If we predict it wrong, we're going to lose a lot of money. So predicting the price is very important, especially for the short-term traders. So the investors use, there are two ways to predict the price, basically. One is the fundamental analysis, which predicts the price in the long term. And they actually predict the value of the shares, and the investors actually use it. And another way is the technical analysis, defining the technical indicators. So they see the trend and momentum of the share price movement with obviously the values, but they can predict in the short term better. So my motivation is to predict the price in the short term because short-term prediction and short-term trading has become automated. According to some news channels, 75%, more than 75% high-frequency trading is done automatically nowadays. So it's actually a thriving market right now. So I want to predict two things: how much it is going to change and which direction is going to change. This is one of the benchmark I used. Currently, we can see that its F1 score is 76.58% for predicting next day share price, and its direction, basically the direction. And my result is like 86%. I'm showing the result to involve everybody, basically. We'll discuss the result later. So I collected the daily data from Yahoo, and it's all the S&P 500 shares, basically 470 of them. Why that 471? Because I wanted a complete set of data. So if the share has complete set of data for these 5 years, I got this. The share doesn't have a complete set of data, I didn't use this, but 470 is good enough. I used Google Colab and Python 3 environment, and for deep learning I used TensorFlow network. So one of the things about the data, or some of the things we'll see about the data, this data is auto-correlated. That means today's price has a correlation with tomorrow's price. And this creates a lot of problem training the models. What happens is the loss function output becomes very less, and it doesn't optimize very well. But it is one of the major reasons I used slightly different technique, which I'll share. This is roughly what we have done: collected the data, and then defined basically some trends, and defined the secondary data, which is basically the returns and log returns from the share price. Return is nothing but how much it grew, the movement of the share. And I got the trends of the movements. So I got the trends of the share price, and I also got the trends of the movements. And then I concatenate all of them and prepare input set, train the models, and predict the price. This just to understand how these things are done. So the trends, what is a trend? A trend is like overall trajectory of the data. That is, it's showing that it is going up or down. Basically, it is done by smoothing the time series data. Different kind of smoothing techniques like moving average, exponential moving average. But what I have used is called Wavelet Transformation, which is used in signal processing a lot. This is the Wavelet Transformation. It is also smoothing. We can see this in this graph. Wavelet Transformation is almost similar to Fourier transformation. It transforms the signal into a frequency space, but Wavelet keeps both frequency and time scale, time domains. But Fourier, what it does is it converts the data into frequency only. But Wavelet have both of them, and it has this a distinct improvement that it can capture the transients very well. So this is these two graphs I'm showing. In the top, the blue line is the actual series. The red and green lines are moving average and exponential moving average, and the orange line is the wavelet transform data at resolution 5. Two things I want to stress here. One, this is a price data, so we can see the trend very well with our human eyes. It's going up and down. Looks pretty. Second thing I want to show is the orange line is always leading the green and red lines. That means this wavelet is smoothing, actually leading the trend or going with the trend. But the moving average, exponential moving average, always goes behind the trend. It cannot capture the trend. It always comes later. To show that on the chart below, I moved the wavelet transformation for 20 periods, and it showed that it matching with the other trends. This is the trend for price changes, price movement. Now, from previous one and this one, it shows that the price movement is a bit chaotic. With the human eyes, it's very hard to point out any trend here. But what I have seen in my experiments is that the price trend, if we train the model with price trend, it doesn't give very good value results. If we train with this trend, with the price movement trend, it gives very good value. We can't see the trend here, but the LSTM networks kind of see the trend here. They can capture the trend from here. One of the method I have used is PCA, is like changing the dimension to the highest variance. It reduces the dimension. That helps us train the models better. Now the neural network, I'll quickly go through it. It's a neuron, is a artificial neuron, is trying to mimic the human brain cell that captures data and multiplies the weight, and it activates. And thus we can do some computation with it. We can also make a network of neurons, which is also similar to the network of brain cells. Now, a network of brain cells takes a vector as an input and gives a vector as an output. What if we have a trend? How do we input the trends and then get an output of a trend or output of one value? We use a recurrent neural network for that. A recurrent neural network can be architected as a chain, and we can input a trend in a different in a chain as a sequence. And what happens is consecutive recurrent neural network cells or RNN cells can share the knowledge what happened before, and thus the previous value or the previous result impact the current result, and that's how it can learn a good amount of trend. But RNN is a little bit earlier, and it has some gradient, vanishing gradient problem. To resolve that, researchers come up with another recurrent neural network, which is LSTM. And we can see the recurrent neural network trains only 2 values. LSTM is obviously training 7 values, which is a bigger one. Same picture, what we have done. Now we made the data into an input series. So we are inserting 25 different data points in the LSTM to identify what would be the next price change in the future. And we came up with different data sets from the same price trend and 3 different models. These are my data sets, like 7 data sets. And these are the 3 models. This is a simple neural network. The middle one is a little bit complex with lots of batch normalization, and the third one is without a batch normalization. All of them get the same inputs, but this is the result. We can see that model 1 on the top left corner and model 3 on the top right corner performs best. They have 86% accuracy of determining next day price move, but model 2 a little bit late. And dataset 3 and dataset 4 performs the best, and they are the series of return. That means the series of price movement and the log returns. All of them has a wavelet transformation. So this is the result again in a tabular format. You can see that return and log return produces almost the similar result. But the model 1 works better with the log return, whereas model 3 works better with the return values, the raw return values. This is the discussion. So model 2 performed well, but it is not comparable. It is a little bit less comparable with model 3 and 4. What I'm trying to find here is model 3 has a distinct connection, which I'm calling as the residual connection. It is inspired by residual neural network. So if we do it in one pass, it tends to like overfit. If we have a residual connection, it kind of provide a consistent outputs. And when I checked the training values, the model 1 always gets overfitted. But the model 3's output for training and testing is almost similar. So that proves that model 3 is actually a better one. Similarly, I have shown that the precision recall and F1 values are always consistent for model 3. And model 1, though its values are good, but it didn't produce that similar consistency. This is one of my outputs that we can see that the price movement trend and predicted price movement trend are similar. The blue ones are the actual price movement trend, and the orange one are the predicted price movement trend. There's some spikes are there, which is the problem. And when we add the predicted price with the current day price, we get the tomorrow's predicted price. And we can see few sharps there, which we can improve in future. So this is the discussion again. So we see that wavelet denoising, it works when we use it, it works better. And we have seen that when we use the price movement trend instead of the price trend, the model learns better, probably due to the autocorrelation of price, but price movement doesn't have any correlation. So that one. And thirdly, we have seen that if we use a residual connection for the LSTM network, its values are more consistent, both in training and testing, and all three, like accuracy values, as accuracy metrics is more consistent. So these are my findings. Here is the training and test accuracies that I have seen. We can see that model 3 training and test accuracies are always similar. Model 1 and model 2 training and test accuracies are different. So future work, a lot of work can be done in future. One is using a trading strategy to trade with it. Secondly, the point I'm stressing is movement trend works better with LSTM than price series trend itself. It would be a good idea it would be a future work to check whether that is true for all other sort of time series. Like a lot of researchers are using the time series itself instead of the differences. We can check it out whether it's true for all different type of time series. Yep, that would be the discussion. That will be end of my presentation.
Thank you, Shu.
Thanks. Thanks for listening.
Any question? Can you just explain what F1 score is?
F1 score is like made from precision and recalls. So precision is how much we have predicted. Let's say we have X amount of element, how much we could predict it correctly. And the recall is how many of precision is how many we have predicted is correct, and recall is how many we have predicted from the correct ones. And F1 is basically a combination of these two.
One question. What is the biggest challenge that you had facing in this project, and what did you do to counter it?
So from my point of view, the biggest challenge was a set of data, because we are using the LSTM, which is deep neural network. It requires a lot of data, but we have used the daily time series, which is only 1200 or 1500 for a particular shell, which can be considered a very less amount of data for learning deep neural networks. So I have resampled the data basically to make the data sample bigger. But yeah, it is a problem. it is still a problem, which it requires a lot of data. Second one, I would say that I was always using the price trend instead of price movement trend. And first, for a long time, I used that and tried to see whether it can improve, but it doesn't improve that much. Because of the autocorrelation, what happens is the loss function gives a very small amount of loss, because today and tomorrow's price are almost the same. Let's say if we predict today's price as tomorrow's price, it is already 99% correct. So the loss function output is very less, and we use the loss amount to retrain the network or optimize the network. If the loss amount is very small, the optimization doesn't go. Optimization doesn't happen that much. But when I started using the price movement trend, it is not correlated at all. Today's price change is not correlated with tomorrow's. So it predicts very well, like it trains very well, and can capture those hidden secrets in the hidden trends in the price movement. What we as a human, we cannot comprehend those things, but the network can actually pick those up. So these two things I think would be the biggest learning for me.
Okay. I may have missed the first part of your presentation, but did you include technical analysis in your data set?
No, not at all.
Any more questions?
You just mentioned PCA in your slides.
Yes.
Could you briefly talk about how you apply that?
So PCA, I have applied. I have shown different data sets for the interest of time. I didn't go in the details of it. So one of the conception is like all the prices in the market basically influence that tomorrow's price change. So I captured all the price change of all the S&P 500s, and it is like then becomes a 470 data points. So I used PCA to summarize those market trends instead of one single price trend. Like the share I'm predicting, along with that, I used all the market trend, and for those market trends like 470 share prices, I use PCA to summarize it to only 10 PCAs to capture the market trend.
All right, so if there's no more question, we thank Matloob. Thank you.
Thank you very much. Thank you for listening.